Alright, in this exercise we're going to discuss heater actuators and how differences in actuators would affect our models. So we're going to discuss the TCLab and how the TCLab works. The TCLab works using pulse width modulation, fancy word, with these heaters. These heaters are actually transistors, and that resistance, the electrical resistance, translates into heat. It's not a typical way to have a heater, but it works for us to communicate between the Arduino and this analog signal, or at least simulating an analog signal. It does so 500 hertz, or every 2 milliseconds. It cycles from 0 to 100%, and those little signals are those pulses between 0 and 100% are how it transmits 8-bit signals. So the transistor heat can be set between 0 and 100 for both transistors, but we're going to be curious if that has the same effect. So go ahead for we should lab.q1 65. Let's do this. Let's add this to this real quick. We want to print the temperature before and afterward. So we're going to go lab.t1 without the semicolon, and then lab.t1, and then let's do that again for q2. Lab.t2, pause 5, lab.t2. So go ahead and do this for the sake of that we were told to, if nothing else. You can connect your USB that supplies power to a computer. You may have noticed there's not actually as much power coming from your computer normally, but you can do that. Either way, the power gets transmitted into a voltage signal, and that voltage signal is then transmitted into a different heat setting. You could actually go, if it's between 0 and 100%, the signal could be a maximum at 255, but our hardware sets limits. So for heater 1, 100% is a signal of 200. And for heater 2, 100% is set to a signal of 100. Now they're the same heaters, but we do that so that heater 1 and heater 2 are different, so we can look at different effects. If we look at the temperatures, temperature before and afterward, heater 2 actually gained heat, it looks like, or lost heat, I should say, over those 5 seconds, whereas heater 1 increased about, I don't know, 0.3 of a degree. So the point here is that heater 2 is about half as powerful as signal heater 1. If we look at the input signal of 100% to the output signal to the Arduino. And so we're going to be asked now, given the FOPDT constants below for heater 1, determine what the FOPDT constants for heater 2 would be. And so I'll do this with my mouse, because let's think this through. It shouldn't be that hard to think about. And I think gain is the perfect way to think about it. In fact, let's think of it another way. Get out my handy dandy marker. So if we think of gain is equal to out over in, that's the way I always think of gain. We have some input, and it's what that output is. It's the conversion to the next thing down the line. So if we think of our signal to that percentage signal is then going to go to the thing that translates it into a signal that is then sent to the heater. Which is then sent to make heat. I don't know, we'll say Q for heat. And we know that, and so this we'll say this is Arduino. So there you have it. A percentage signal is sent. This is let me change colors. Do like a good blue. So this is between 0 and 100. This is then goes to, I'll do it up top, 0 to 200, or 0 to 100 for heater 2, and that then goes to some heater setting which then produces power. So let's think about this. In the case of heater number 1, we know that in comes some percentage power, and out is 0.9 delta C, degrees C, that's what that is right there, per percentage power. I'll say percentage P. The only thing that changes between heater 1 and heater 2 is the magnitude of the signal sent. So if we think that through, the magnitude of the response is going to be half, then we know that this should be about 0.45, because this magnitude right here is half as much. So 0.45 degrees C per percentage power. Now the question is, will that change the process time or the dead time? What determines each of those? Well, the dead time is just determined by delay between the signal being sent and a response. That shouldn't be different, so that should be equal. The process time is how long it takes for the response to equal to get to the steady state condition. What's that determined by? Well, in our sensor and heater system, it's determined by the heat capacity of the heater. Now the heaters are the same size, and so energy in will change the temperature at the same rate for both heaters. So that should be the same as well. So the only thing that will change then is the gain. Now, I was cheating. I've done this before. If we look at things though, we have Kp1 equal to 0.9, tau P1, and theta P1. These are just the constants from before. And if we have a heater 2, our guess is that it's going to be half as powerful, so the gain is going to be half as much, but the other two constants are the same. Now we're going to test this with our temperature control lab and see if we're right. We're going to go ahead, we're going to set our arrays for storage like normal, and we're going to set some arrays for predicted as well as simulated temperatures. Then we're going to use this try block, so if anything happens, we'll quit. If we look at the very end, we just make sure we turn off the lab, turn off the heaters, and clear the lab. So this is a good programming practice for you to learn these try-catch blocks. So if there's some error that happens here, it will default to the catch. So what we're going to do then, we set tick somewhere. We should have, looking for a tick, right here. Here's a tick. And then right here, we're going to record the time. We're going to record the change in time. We're going to record the temperatures. And we're going to implement the heater settings. Right here, we have some changes in heater values. And we'll look at the change. We're going to simulate the time step with the FOPDT explicitly. We're going to use the integrated form of the FOPDT equation to get us some output based on those FOPDT predictions. And so that's where those will be stored within these predicted arrays. And then we'll have a plot showing the actual and predicted temperatures. And then finally, we'll pause for the remainder of the second. So we'll go on, let's go ahead and run this. Make sure there's no errors. I guess I could make sure I'm showing the whole screen, or the whole line. And it looks like we're off to the races. So let's go ahead, I'll make this big enough for us to watch. And I'll go ahead, I'll just pause it for the video's sake, and we'll discuss the conclusions afterward. Just popping in to let you know I caught an error. Happens to the best of us. And that caused another error, so let's go ahead first. Let's just make sure lab.off. Spelled it wrong. Lab.off. Make sure, okay, let's go. Lab is equal to TCLab. Do we have a connection? Seems like we do. Lab.off. Clear lab. Clear all. Close all. Point is, and I'll say this for simplicity's sake, there should be a hold on right here. I noticed that one wasn't plotting. So we're just going to go ahead and change that. Hold on. That way we plot everything. So I'll go ahead and fix that and reset the timer. We'll see on the other side. And there we have it. So it's graphing. We'll see when it's done simulating. All right, let's take a look at this. So our FOPDT is predicting temperature 1 and temperature 2 with these step changes that occur. We can see they did a pretty good job on temperature 2, as well as the degree of change in temperature 1. You know, it changed, I don't know, it looks like about 15 degrees. And it looks like that lines up pretty well as far as the magnitude. Obviously, it started at just after 300. At 300, it was turned on. We did a pretty good job at anticipating the dead time. But it started at a higher temperature. We anticipated the starting temperature to be 23. Because of temperature 2 being on, it actually started at, I don't know, let's say 27. So because of that, it increased starting at 27 up to maybe 40, maybe just below. But it looks like we did a pretty good job. And so what's our lesson here? The actuator magnitude determines the magnitude of the FOPDT gain. Why is that? The FOPDT gain represents the change in output based on the change in input. And if we think about that, our magnitude of the actuator is our change, and it causes the output change. So that makes sense. So hopefully this has been a good, helpful lesson. I'll just say this as we close with actuators. Engineers are valuable because of their ability to understand the actual physical phenomena as well as model them. If you can only model but you have no idea what's going on, you're not all that useful. And so being an engineer with an intuition about what's going on is what makes you valuable. All right, let me know if you have any comments, questions down below.